Hello and welcome back to the module 2 on loaders and linkers. Earlier in this module we have discussed the basic functions of loaders and we have seen the design and implementation aspects of a simple absolute loader as well as a special type of absolute loader, namely the bootstrap loader. In the upcoming 2 sessions I'll be discussing the machine dependent extensions to the basic loader functions. And here we will examine the issues of relocation and linking from loader's point of view. So in this process, we will discuss the design and implementation aspects of relocating loaders that provide for program relocation, as well as linking loaders, which are advanced loaders typically found on most modern computing systems. In this session, I will be exclusively focusing on relocating loaders under machine-dependent loader features. So earlier in our discussions on the basic loader functions, we have seen the design and implementation aspects of absolute loader. And we have seen that the functions of absolute loader are rather simple, as such loaders need not perform complex functions such as linking, relocation, etc. The functions of absolute loader involves moving translated instructions and data into the memory at the specified absolute address and initiate execution. However, despite the functions being simple, absolute loaders have certain shortcomings. One obvious drawback of absolute loader is the need for programmer to specify the actual address at which the program will be loaded into memory. This doesn't create much difficulty on very simple computer with smaller memory such as with SIC. However, on larger and more advanced machine, it is often expected to run several independent programs together, sharing memory and other system resources between them. Which means that we do not know in advance where a program will be loaded. Or we should be able to load the programs wherever there is room for it. However, efficient sharing of machine requires that we write relocatable programs rather than absolute ones. However, the absolute loading scheme doesn't provide for program relocation and requires that programs are assigned absolute addresses. So another difficulty is the use of subroutine libraries effectively. Generally, most libraries contain many more routines than will be used by any one program. In order to make efficient use of the memory, it's important that we are able to select and load exactly those routines that are needed. But this cannot be done effectively if all subroutines have pre-assigned absolute addresses. Or in other words, it requires that subroutines are relocatable. And again, the absolute loading scheme does not provide for program relocation. So in this session, we will be discussing alternative schemes for loading, or in other words, we will discuss more complex loading schemes which addresses the issues of program relocation and linking. First, we will discuss the design and implementation aspects of relocating loaders, which provide for program relocation in addition to the basic loading functions. Also, in this process, we will discuss the effect of machine architecture on the design of the loader. And we will see that the way relocation is implemented in loader is dependent on machine characteristics. Thereafter, we will discuss the design and implementation aspects of linking loader, and we will see that it employs same implementation techniques as relocating loaders, as generally linking involves relocation of some of the routines being linked together. So in this session, I will exclusively focus on the design and implementation aspects of relocating loaders. The concept of program relocation was earlier introduced in Module 1 under machine-dependent assembler features. And you are already aware that the need for program relocation is an indirect consequence of change to larger and more powerful computers. On larger and more advanced machine, it is expected that several independent programs are run together, sharing memory and other system resources between them, which means that we generally do not know in advance where a program will be loaded, or we should be able to load the programs wherever there is room for it. So thus, the actual starting address of the object program is generally not known until the load time, as with the absolute loaders, which means that we write relocatable programs rather than absolute ones. And the loading scheme provides for program relocation. So such loaders that allow for program relocation are referred to as relocating loaders. Also, relocating loading scheme allows efficient sharing of memory in larger machines where several independent programs have to be run together, and they also support the use of subroutine libraries effectively. So before discussing the design and implementation aspects of relocating loaders, we will discuss the common approaches for specifying relocation as a part of object program. So already in module 1, while the program relocation concept was discussed, you were introduced with one approach for specifying relocation as a part of object program. That is to allow for program relocation, or to allow the object program to be loaded at a location different from the address specified at the assembly time. It's important that we identify those portions of the object code that requires modification when the program is loaded at an address different from the address used during the assembly time. And this information can be included in the object program, or this information can be communicated to the loader in the object program via the modification record technique. We have already seen one approach, what is known as the modification record technique, and we have seen how to generate the object program for SIC-XC instructions by identifying those portions of the program that require modification, employing modification records. So we have already seen that in SIC-XC, the only instructions that require modification are the 4-byte instructions. You are already aware that SIC-XC provides for 4 different instruction formats: the format 1, format 2, format 3, and format 4, which are 1 byte, 2 byte, 3 byte, and 4 byte instructions respectively. The 1 byte instruction does not make any direct memory reference. They do not have any operands as part of the instruction. Format 2 or 2 byte instruction uses registers as operands, while the format 3 uses relative addressing and encodes displacement as a part of the instruction, while the format 4 instruction specifies direct address, that is the address of the operand, as a part of the instruction. So the only instruction that requires modification are the 4-byte instructions. So apart from this modification record technique, we will be discussing in this section an alternative scheme for specifying relocation, namely the relocation bit technique, considering SIC programs, wherein instead of using the modification record technique, each instruction is associated with the relocation bit, which indicates whether the instruction requires modification or not. So before discussing in detail the alternative scheme, that is a relocation bid scheme for specifying relocation, we will just refresh the modification record approach for specifying relocation as a part of object program. So to identify those portions of the object program that requires modification, we have seen that the modification record technique can be used. And in this scheme, we identify those portions of the object code that requires modification by specifying the starting address of the field that requires modification in columns 2 to 7 of the modification record, along with an indication of the length of the address field that is to be modified in half bytes. Further, we also include information about the modification that is to be done, which is indicated in the modification record via modification flag, indicating whether we have to add or subtract the value of the external symbol to do the necessary modification. So we will consider an SIC-XC program and see how relocation information can be communicated to the loader in the object program. Relocation cannot be accomplished by assembler because assemblers at the assembly time do not have any information as to where the program will be loaded in the memory. Loading is done by a separate system software, namely loader, and the assembling is done by the assembler. So assembler has to identify those portions of the program that require modification to the loader in the object program. And for SIC-XC programs, we have seen that we can use modification records to identify portions of the program that requires modification. Now with this introduction, we will now see how to write or generate a relocatable object program for the source program. So the program is named copy and it uses two subroutines, rdrec and wrec. So in the source program, you may see that certain instructions are marked or underlined, and these instructions indicate the 4-byte instructions which require modification if the program is loaded at a different address. You may see that the instructions are indicated with the plus sign indicating that they use extended format or the 4-byte format. Any instruction which is prefixed with plus sign indicate that the instruction has to be assembled using the 4-byte format, and the 4-byte format specifies the address of the operand or the direct address of the operand as a part of instruction, or in assembling the instruction we use the direct address of the operand. So we see that the instructions have to be loaded at the relative address 6. The instruction on line number 15 has to be loaded at the address 6, while the instruction on line number 35 will be loaded at the relative address 13. Likewise, the instruction on line number 65 will be loaded at the relative address 26. So these are relative addresses because their values depends on the starting address. For assembly purpose, it was assumed that the starting address is 0. However, if an attempt is made to load the program at a different address, then the starting address will change, and likewise all these addresses will change. That is why we refer to them as relative address and not absolute values. As you see here, each of these 4-byte instructions involves a reference to the symbol rdrec and wrec. rdrec has the relative address 1036, while wrec has address 1058. Again, these are relative addresses, and the location counter value here indicates the address corresponding to wrec, with the assumption that the program load address, or with the assumption that the starting address is 0. Now, if we try to load the program at a starting address 5000, then we need to add 5000 to 105D, so that the address associated with WREC will be 605D. So in assembling this instruction, the address of the operand will be used, and this address is specified in the last 20 bits, or in the hexa representation it is indicated in the last 5 digits. The 4-byte instructions use direct address as a part of the instruction. The first byte indicates the opcode for JSUB. The opcode for JSUB is 48, and we have N and I set to 1 here, as the instruction neither indicates immediate nor indirect addressing. So N and I are both set to 1. So 48 plus 3 will be 4B. This is the first byte. The following hexadecimal digit 1 indicates the setting of flag X, B, P, and E, which are all set respectively to 0, 0, 0, 1. E is set to 1 because we use the extended format. And the last 20 bits, or the last 5 hexa digits here, indicate the address corresponding to RDREC. We see that the address corresponding to RDREC is 1036, which is a relative address. And if we load the program at a different address, the value for RDREC will change. And in such case, we need to add the starting address of the program to the value corresponding to RDREC. That is, we need to add the actual starting address, or the actual load address, to 01036. And the same applies to the remaining instructions at line number 35 and 65. We now will look into each of these instructions and see where exactly are these instructions loaded in memory. So consider the instruction in line number 15. The opcode is 4B101036. So you may see that the address assigned is the relative address 6. So 4B will begin in the memory at the address 6. The address corresponding to the operand field, that is RDREC, will be placed in the memory in the immediate next location. Likewise, if we consider the second instruction, that is at line number 35, the starting address here is 13, wherein 4B is stored. Similarly, for the instruction in line number 65, the opcode, that is 4B, will be placed at the address 26. And we see that the operands which indicate the address corresponding to RDREC and WREC has the value 01036, which will begin in the memory at the immediate next location. 4B is at the address 06, will be loaded in the memory at the address 06, while the rest will be placed starting from 07. Likewise, for the instruction on line number 35, 4B will be placed at the relative address 13, and the rest will be starting at the address 14. So the address field, that is address corresponding to WREC, will be placed in the immediate next location following 13. Likewise, for the instruction on line number 65, the address corresponding to WREC will begin in the memory at address 27. So these addresses are important because if the program is loaded at a different address, then we need to add the actual load address to these values, which begin in the memory at the address 7, 14, and 27 respectively. So this information has to be indicated in the object program so that the loader is able to do the necessary modification at the time of loading when it gets the actual load address. So we will look into the object program now. This is the object program generated for the program copy. As you see, it has a header record with the name, starting address, and length. And we have a series of text records wherein the object codes are placed. And I have identified those instructions which require modification which is highlighted in green, blue, and yellow, corresponding to the instructions on line number 15, 35, and 65. So these are the instructions that are generated which require modification, and the corresponding modification, or the portions of the code that requires modification And what modification has to be done is indicated via the modification record here. Actually, these are commands to the loader. When the loader loads the program, it does the necessary modification that is indicated in the modification record. So the modification record for the first instruction, that is for the instruction on line number 15, says that to the field that starts at the address 7, which is 5 half bytes in length, add the actual address of copy. Currently, we know that the value for copy is 0. This is a relative address. This is not the actual address. So actual address for copy is obtained by adding to this the actual load address, which is obtained at the time of loading from the operating system. So this says to the field that starts at the address 7, add the actual value of copy. So it means that currently at the address, at the memory location 7, we have 01036. But this 01036 is only a relative address corresponding to RDREC. If we load the program at the address, say 5000, then we have to add 5000 to 01036 so that the address changes to 06036. So the modification record says to the field that starts at address 7, which is 5 half bytes in length or which is 20 bits in length, we need to add the actual load address. The actual load address corresponds to the program name, or it corresponds to the symbol copy, which is obtained by adding to the current value the actual load address. So this is for the first instruction. Likewise, the second modification record corresponds to the instruction on line number 35, and it says that to the field that starts at address 14, which is 5 half bytes in length, add the starting address of the actual starting address of the program. So getting back, so to the field that starts at address 14, the field that starts at 14 is 0105D. To this field, we need to add the actual value of copy, which will be obtained at the load time. Likewise, for the third instruction, we need to say that for the field that starts at the address 27, add the actual value of copy, actual load address, that is the address corresponding to the symbol copy. So you may see the last one says to the field that starts at 27, add the actual value of copy. So now, having generated this object program wherein the portions of the program requiring modification have been identified to the loader via modification record, we next need to see how such an object program, how this relocatable program is processed by a relocating loader. So I have a question before proceeding ahead with the discussion on the relocating loader. I have a question. So we have in line number 133 a 4-byte instruction LDT hash 4096. So the question is, earlier we have seen that all 4-byte instructions will require modification. Now the question is, does this instruction require modification? So reason out whether this instruction requires modification. If yes, why does this instruction require modification, and if not, why not? Further, I also want you to answer. Now, if your answer is yes for this, then what will be the modification record for this corresponding instruction? Please note the object code is 75101000. So, if your answer is yes, if you say that the instruction requires modification, please show the modification record corresponding to this. And if your answer is no, you can just ignore generating the modification record, because we don't need the modification record in such case. So just now we have seen that modification record can be used to indicate or identify to the loader those portions of the object code that requires modification in the object program. And we have seen that the modification describes the part of object code that has to be changed if the program is relocated or if the program is attempted to be loaded at a different address. And we have seen that the only instructions that use extended formats on line number 15, 35 and 65 requires modification. all the remaining instructions do not require any modification, because we have encoded the instructions on line number 15, 35 and 65 with the absolute address corresponding to the address of the operand, and the values change if the program is loaded at a different address. And also we have seen that the modification record says that we have to add the value of the symbol copy, which corresponds to the starting address of the program. At the assembly time, copy has a relative address 0. So the actual value associated with the copy will be known only at the load time. So at the load time, the value for the symbol copy will be the relative address 0. Where does this 0 come from? So you have already seen at the time of assembly, copy has a value 0. So actual value of copy can be computed as the relative value 0 plus the actual program load address. Okay, so 0 plus the program load address will be the program load address itself. So it means that to do the modification, we need to add the program address to the data that is in the location that is indicated, whose address is indicated here. That is, I repeat this again. To do the modification, we need to add the actual program address, program load address, to the field whose address has been indicated here. So with this explanation, we'll now see how a relocatable loader works in loading this relocatable program into memory. So at the top right, you see, at the top of the screen, you see a segment of the object program, and the program is relocatable. As you see, there is a modification record. Actually, this is the same object program that we have just discussed. The program begins with a header record, and there are a series of text records, and then a series of modification records, and finally there is an end record. So the header record specifies the program name copy, starting address 0, and the length is 1077. And the instruction that requires modification, one of the instructions that require modification is in line number 15, and the code is 48101036. The modification is indicated here via modification record, which says that to the relative address 7, which is 5 half bytes in length, add the value of copy. We have already seen adding copy is same as adding program address. So at the bottom, we see the representation of memory, and you see that the rows represent addresses and the columns represent the consecutive addresses. So the first cell is 0, the next is corresponds to the address 0, the second cell corresponds to address 1, while the third corresponds to the address 0002, and so forth. So we'll now look into the algorithm for SICXC relocatable loader. The first step involves getting the program address from the operating system. So what is this program address? This represents the actual address where the program has to be loaded into the memory. So first step is fetch the program address, and this address is generally supplied by the operating system. So once the program address is known, the records from the object program has to be processed one after the other. So until the end of the input is reached, one after the other records have to be read, and the records fetched has to be checked for record types to see if it is end record, text record, or modification record. So if it is an end record, then we fetch the next record, while if the record type is T, the loader requires to move the object code from the record to the location program address plus specified address. So please note, in the object program, every text records includes the object code that is to be moved, and the address where the object code has to be moved is indicated here. But this address is not the actual address but a relative address, which means that this is the address relative to the beginning of the program, assuming that the starting address is 0 when the assembling is done. So we need to calculate the actual address where it is to be loaded by adding to this the program address. So if the record type is T, move the object code from the record to the location program address plus specified address. Here specified address means the address that is specified in the text record. Every text record specifies the starting address from where the loading has to be done. But remember, this is not the actual address. To this we need to add the program address, and at that location, at the resultant location, we have to move the object codes. So this is regarding the text record. When the text records are processed, object codes have to be moved from the record into the location program address plus specified address. Now, if the record type is M indicates the modifications to be done if the program is loaded at a different address. So what is the processing that the relocating loader has to do if the record type is M? So if record type is M, the loader needs to add the program address at the location program address plus specified address. So we'll get back to the modification record. So if the record type is M, then the relocating loader will have to add the program address. Program address is fetched from the operating system. So that address has to be added at the location that is specified here plus the program address. So at the location program address plus specified address, we need to add the program address. So we will now see how this works. So initially, we have not reached the end of the input. So one after the other, the records are fetched. First, the header record is fetched. And if the record, once the record is fetched, you check if the record type is E. If it is not E, read the next input record. So after the header record is fetched, we check if the record type is E. If not, we fetch the next record. So record type is not E, so we fetch the next record. But before that, before we read the records, please note we need to get the operating. The loader needs to fetch the program address from the operating system. And for the example purpose, let me assume that the program address is 5000. So now after reading the header record, since the record type is not E, we fetch the next text record. The loader fetches the next record. As a record is fetched, check if the record type is T or if it is M. If it is T, move the object code. If it is M, do the necessary modification. So since in this case, the record type is T, the object code has to be moved. And the object code begins here, and you may see that the first code is 17. And where is this to be moved? This is to be moved to the location program address plus specified address. Okay, so move the code 17. Move the code 17 to the location program address plus specified address. So program address is 5000. The specified address in the text record is 0. 5000 plus 0 is 5000 itself, which means 17 has to be loaded at the location 5000. So 5000 plus specified address is 5000. This is a program address. This is a specified address in the text record. So at the location 5000, 17 is moved. Likewise, the remaining object codes will be moved in subsequent memory locations. So one after the other, remaining codes are moved. So by the time the end of this record is reached, so once the end is reached, check if the record type is not E. If not, read the next record. So we are already done loading till here. So since we have reached the end, see if the record type is E. If it is not E, read the next record. So the next record is read, and the record here is of type T. For every record read, it is important to check if the record type is T or M. So here the record type is T. So again, move the object code from the record to the location specified address plus program address. So we will see how the loading proceeds. So the text record specifies the address 1D. So object code has to be moved. The first code is 0F, which has to be moved to the location specified address plus program address. So to the location 5000 plus 1D, that is 501D, we have to move the first object code in this record, which is 0F. So 0F is moved here. It is 5000 plus 1D, 501D, that is this location. Subsequent object codes have to be moved likewise. So all the remaining codes are moved. So we will assume that all other remaining codes have been moved, and then the next records are moved. So assume that the remaining records are also text records. So all object codes will be moved into the memory in the same way. So now at this point, after the object codes from the previous record has been moved, the next record is fetched as usual. So each time a record is fetched, it is important to see if the record is T or E or M, right? So here the record type is M. So each time a record is fetched, you have to see if it is T or if it is M. So if it is M, then the modification has to be done at this point. So modification is done by adding the program address at the location program address plus specified address. So please note, in the modification record, in the example, we see that the modification record says add copy to the location that is specified here, which is 7, which is 5 half bytes in length. But in the algorithm, you may see that it says add program address. Already we have discussed, we have seen that copy has the relative address 0, and we have assumed that the program address is 5000. So the actual value for copy is relative address plus the program address, which is 0 plus 5000, because program address is 5000. So 0 plus 5000 is 5000, which is equal to program address. So adding copy is same as adding program address. So you may see that in the algorithm they have specified program address, not the name of the program. Okay. So this means that this is actually the starting address of the program itself that is to be added. And where do we have to add it? It has to be added at the location specified address plus program address. Specified address is 7. 7 plus program address, which is 5000. At the location 5007, we need to add what? We need to add program address. So we'll get back. We were currently processing the modification record. Now when the loader sees this record, since the record type is M, it adds the program address at the location program address plus specified address. So we will see now how this works. So add at the location program address plus specified address the value of program address. So we know program address is 5000. The specified address is 7. So at the location 5000 plus 7, at the location 5000 plus 7, so at the location program address plus specified address. Program address is 5000, specified address is 7. At this location, what do we need to do? We have to add the value of copy, or in other words, we need to add the value of the program address. So the resultant address here, at the location 5000 plus 7, which is 5007, and at location 5007, what do we have? We have the code that starts with 10, right? But then the modification record also says to the field which is 5 half bytes in length, you have to add the program address. The 5 half bytes in length means that here it is 01036, which starts at the address 5007. So to the field that starts at specified address plus program address, which is 5007, here we have 01036. What do we need to add? We need to add the program address, right? So in this location we have 01036. To this field you need to add the program address. Program address is 5000. So 1036 to the data which is currently here, we need to add the program address so that it gets modified to correspond to the actual address of the operand, which is 1036 plus 5000, which is 6036. So you may see it. So this instruction, when processed, causes the previous content at this location, that which was 1036, to be modified to 6036. So that is all about the relocating loader. As you see, initially the program address has to be fetched from the operating system, and as long as it is not the end of the input, Records have to be fetched one after the other, and the record has to be examined for types to see if it is E, T, or M. E indicating the end record, T indicating the text record, and M modification record. As long as it is not end of the record, the next record is fetched. For every record fetched, since the relocating loader needs to perform the loading as well as relocation, it needs to see if the relocation is to be done or moving has to be done, or if the loading has to be done. Loading is done when the record type is T. And how is this done? It is done by moving the object code from the text record to the location that is specified in the text record plus program address. So remember, in the absolute program, the object code is always moved to the specified address. Whereas since this is a relocatable program, the object code has to be moved not to the specified address, but to the location indicated by specified address plus program address. Likewise, when the record type is M, the modification has to be done, and the modification here indicates that at the location that is indicated in the modification record plus program address, we need to add program address. So the relocating loader will add program address at the location program address plus specified address. So this is to be repeated for every text and modification record. And when the end record is fetched, the next record will be read, and see every time you need to see, because when it's possible that a relocating loader is submitted with more than one object programs. So please note that this does not end when you see an end record, because after the end record you may have the next object program that is to be loaded. So the process will continue until the end of the input is reached. So now we have seen how to specify how to specify or identify portions of the program that requires modification for SIC XC programs, wherein only instruction that requires modification is a 4-byte instruction. Now the question is, does this modification record technique of specifying relocation fit for SIC programs as well? So you need to just go back and understand how an instruction is assembled in an SIC program. Remember, SIC standard version does not use any sort of relative addressing. The instructions there do not use immediate addressing or indirect addressing. We have only two modes of addressing there, direct and indexed. And you may see that since we use the direct addressing, the address of the operand is assembled as a part of the instructions. And all instruction in SIC use the same format, that is a 3-byte format, wherein direct address is assembled as a part of the instruction. So as soon as the instruction is assembled using the direct address, it means that the instruction will require a modification if the program is loaded at a different address. So to understand this, we will consider this. We will answer the question that was posed here later. So consider this SIC program. So the program is named copy. It uses two subroutines, rdrec and wrec. And the program has a relative address 0. It's a relative program. For the program to be a relocatable program, at the assembly time, we always have to consider the starting address 0. So it's assumed that the program is assembled with the starting address 0. So the symbol values are available in the symbol table. First has a value 0, C loop has a value 3, and so forth. And the object codes generated are shown here in the right hand side. The first byte is the opcode, and the last 15 bits, last 16 bits indicate the address of the operand and as well as the mode. Mode is either direct or indexed. All these indicates direct mode, whereas index mode is indicated only when the second operand is a register X. So here we don't have any index mode of addressing. So how do we assemble an instruction? We have STL, RET, ADR. The opcode for STL is 14 and RET, ADR is defined here. It is 0033. So we use this direct address or this relative address in assembling the instruction. So it is 140033. Likewise, you consider any other instruction. For example, consider LDA EOF. So what is the object code generated? LDA has the opcode 00. EOF is assembled using the address 002A. It is 002A. Likewise, you can go through each of the instruction and you may find that every instruction is assembled using the direct address of the operand. Now, all those instructions which have been highlighted here in this box uses the direct address. Coming to R sub, the instruction R sub does not have any operand, so the instruction is assembled using zeros. So here we don't use any direct addressing. Coming to the next instruction which specifies a constant, here the constant EOF is generated, which is 454F46. So this instruction, this code represents the constant and it doesn't change. The next is a constant 3, which is indicated internally using the hexa digits as shown here. Likewise, 0 is encoded as shown here. So please note all instructions which have been shown in the rectangular box uses direct addressing. So what does that mean? If we try to attempt to load this program at a different address, then all this code has to be changed. So let us assume instead of 0, the starting address is 5000. Now, the value for first will not be 0 but 5000. Likewise, the value for C loop will not be 0003, instead it will be 5003. Likewise, end fill will not have the value 0015, instead it will be 5015. And this applies to every symbol that is appearing in the label field here. EOF will have the value 502A rather than 002A. So accordingly, the object code generated will be different. So you may see that the instruction LDA EOF earlier was encoded as 00002A. Now the generated object code will be 00502A instead of 002A. So we will consider another example. For example, consider LDA length. The initial object code generated when the starting address was 0 is 000036. What is this 0036? It corresponds to the length, and the value here was 0036, assuming starting address 0. Now if we assume that the starting address is 5000, then you need to add 5000 to length, so that the address is 5000 plus 36, which is 5036. So please note the object code generated assuming starting address 5000 is 005036. So you see the difference between the two codes. Assuming the starting address 0, this will be the code, whereas assuming starting address 5000, this is the code. So how do we get this code from this code? You just have to add 5000, which is nothing but the actual the load address, to the field which indicates the operand or which represents the operand. So by adding to 0036, the starting address 5000, we will get 5036. So this is a modification that has to be done at the time of loading. But these instructions do not require any modifications. So we have just seen that if we try to load the program at a different address, all the instructions starting at line number 10 through line number 70 has to be modified. The only instructions that do not require modification is R sub and the last three object codes, because these represent constants. 454F46 represents the constant EOF. Likewise, the following code, that is 000003, represents a constant 3 in hexa. Likewise, the last one represents the constant 0 in hexadecimals. So we have just seen that every instruction, every object code that is placed in the object program has to be modified if the program is loaded at a different address. So I indicate those instructions which require modification with ones and those object codes which do not require modification with zeros. So excluding the last four object codes, all others require modification. Likewise, if we examine the subroutine RDREC, excluding R sub and the constants, that is F1 and the internal representation for the constant 4096, all other object codes will have to be modified if the program is loaded at a different address. So this is being indicated here with all instructions with value 1, while all others, all the last 3 have been indicated with 0, meaning that they don't require any modification. So for the subroutine RDREC, excluding the last 3, all others will require modification. Again, moving to the last subroutine, that is WRREC, the same thing holds here. RSub doesn't require a modification. Likewise, the object code 05, which corresponds to the hexadecimal constant 05, doesn't require any modification, while all the rest of the instructions at line number 210 through 240 needs to be modified if the program is loaded at a different address. We have indicated it here with ones. Earlier, we posed a question as to whether the modification record technique can be used to specify relocation in case of SIC object programs. So, as we have just seen, unlike in SIC XE, wherein only the 4-byte instruction requires modification, in the standard version, as we don't use relative addressing and as we don't use register to register mode of addressing or immediate addressing, all the instructions excluding RSub will require modification. So every instruction except RSub and except the constants in the object program would require modification record. So since all the instructions excluding RSub requires modification, the resultant object program would be more than twice as large as the one without modification record. So you see that modification record technique is not very well suited for all machine architectures, particularly SIC. So obviously we need to have a different scheme for specifying relocation in case of SIC programs. So the alternate technique for specifying relocation is the relocation bit technique. So in this scheme, any object code that requires or any instruction that requires a modification is indicated in the object program via relocation bit technique. And here in this technique, we use one relocation bit to specify whether an instruction requires modification or not. You are already aware that in SIC, every instruction is assembled using a 3-byte format. So associated with every 3 byte of object code, we place a relocation bit which says whether the instruction requires modification or not. And the question is how this relocation information is indicated in the object program. So to indicate the relocation information in the object program to the loader, we gather all relocation bits together into what is known as a bit mask. And the bit mask is kept in the text record immediately following the length indicator. You are already aware that text records hold all object codes. In one text record, we keep at the most 10 instructions. So the bit mask for any particular text record should indicate whether the object codes in the corresponding text record will require modification or not. And the bit mask is generally represented in character form as 3 hexadecimal digit. The bit mask is actually formed by gathering the relocation bits together, and it is represented in the character form using 3 hexadecimal digits. So we shall see how to generate the bit mask for the object codes in the text record. So consider the same program, copy. Already we have the object codes generated, and the indication as to whether an object code requires modification or not is indicated with ones and zeros. Let us call this as a relocation bit. A relocation bit should indicate whether an instruction requires modification or not. If the instruction requires modification, then relocation bit will be set to 1. If the instruction doesn't require a modification, then the relocation bit will be set to 0. So The first instruction is STL RET ADR. The object code is 140033. And you notice that written address has the address 0033, which is used in encoding the instruction. So if we load the program at the address 5000, the address for RET ADR will no longer be 0033, it will be 5033, which means the instruction will have to be modified if the program is loaded at the address 5000. So it means that the instruction requires a modification. So we have the relocation bit set to 1. Likewise, all the instructions until the line number 55 here, until the line number 70 requires modification. So the last 4 doesn't require any modification. Now we will see how to gather these bits into bit mask. So as was mentioned earlier, the bit mask is formed by gathering the relocation bits, and each bit mask is indicated by 3 hexadecimal characters. So what do? Is we group the relocation bits starting from the beginning in groups of 4. So the first 4 instructions, the relocation bits associated with first 4 instructions are grouped together. You see that the bits here are 1, 1, 1, 1, indicating that the first 4 instructions require modification. So the equivalent hexa representation for 1, 1, 1, 1 is F. Thereafter, following instructions, that is starting from 300015 till 00002A, we have 4 more relocation bits. So again, we group them together, and the equivalent representation in hexa is F. So after that, we have remaining instructions. But at this point, you need to know that in one text record, we are allowed to place only 10 instructions. So the line here indicates the range or the number of instructions that we are able to keep in one text record. So in the first text record, we can keep instructions from 140033 at line number 10 through the line number 55. The last code is 00002D. Okay, so having grouped the first 4 together, we are left with 2 bits. Remember, the relocation bit mask has 3 hexadecimal characters. With the 3 hexadecimal characters, we can have 12 relocation bits. And a relocation bit is associated with every 3 byte instruction. But since in one text record, you cannot keep 12 instructions, but only 10 instructions, the 2 relocation bits will be unused, or in other words, the unused relocation bits are always indicated with zeros. So after having the first 10 instructions indicated with 1, saying that they require modification, we are left with 2 relocation bits in the text record, because we don't use 12 instructions in one particular text record. So the relocation bit corresponding to unused words has to be set to 0. So that way we have 1, 1, and the remaining 2 unused words are indicated with 0, 0. So 1, 1, 0, 0 is C. So this is regarding the first text record. In the following text record, we will keep the codes from 0C0036 through 000000. We have to stop at this point because the following instruction indicates reserve word, in the sense reserve storage space in the memory starting at this relative address. So we cannot keep object codes that follows in the current text record. We have to stop here, terminate the text record here. So you may see that again we group the 4 relocation bits. That way we have 1110, which is represented with the hexa digit E. Thereafter we have the object codes 454F46, which is a constant indicated with the relocation bit 0. The last 2 are also constants indicated with the relocation bit 0. So we have 1, 2, 3, 4, 5, 6, 7. 7 object codes of 3 bytes length are placed. What about the remaining object codes? They are unused. So the relocation bits corresponding to all the remaining will be set to zeros. That is, the remaining 5 relocation bits will be set to zeros. So now if we group into 4 fours, we have 1110, which is E. 0000 is again 0, and the last 4 relocation bits are also set to 0. That is why the last hexadecimal digit in the bit mask is again 0. So in the relocation bit technique, we associate each 3-byte code with the relocation bit, and the relocation bit set to 1 means that the instruction will require a modification, while the relocation bit set to 0 means no modification is required. If a relocation bit corresponding to a word or a 3-byte object code is set to 1, then the modification is performed by adding the program's starting address when the program is to be relocated. So whenever a relocation bit associated with the word is 1, we need to add the program's starting address to that word if the program is to be relocated. So we will see now how this relocation information is indicated in the object program. As I mentioned earlier, object codes are kept in the text record. So associated with each object code that is kept in the text record, we have a relocation bit, and the relocation bits are gathered together into bit mask. And already we are aware that bit mask represents 3 hexadecimal characters, which means 12 relocation bits. So since in one text record only 10 instructions are allowed, the 2 unused words are the relocation bits corresponding to 2 unused words are set to zeros. And one thing that has to be paid attention here is always a relocation bit is associated with the 3-byte segment. So relocation bit should always coincide with the 3-byte segment. And the relocation bit mask will be kept in the object program in a text record from column 10 to 12 immediately following the length indicator. So we have the object program with the object codes represented here for every instruction, and we have the bit masks shown here in the right hand side. As I mentioned earlier, we group 4 relocation bits together to form a hexadecimal digit. And in one text record, since we are able to keep 10 instructions corresponding to the unused words, we set the relocation bits to 0. So in one text record, we are able to keep instructions from line number 10 to 55. So the relocation bit mask for the first text record will be FFC. Likewise, in the text record, we are able to keep the object codes from line number 60 to 90, and hence the relocation bit here is E, 0 and 0. There are no codes here, which means the corresponding relocation bits are 0, and hence the hexadecimal digit will be 0. So FFC means that all 10 words of object code have to be modified. You see that all relocation bits are 1, so all instructions will require modification. So as I just mentioned, corresponding to unused words, only 10 instructions are allowed. The last 2 are unused because relocation bit mask has 3 hexadecimal digit, which means 12 relocation bits. But here we can represent only 10 relocation bits. Corresponding to unused relocation bits, we use zeros. That is why 1100 is to be represented by the hexadecimal digit C. Moving to the second text record, we have 1110, which is represented in hexa as E. After that, we have 3 constants, but we can group 4 bits together. So the unused next object code is not present here in the text record. So corresponding to that, the relocation bit is 0. So 0, 0, 0, and the unused one is 0. So we have 0. Again, in one bit mask, we can have 3 hexadecimal digits. So we have only 2 here. Corresponding to the there are no object codes as such here. Corresponding to them, the relocation bits will be 0. So the last hexadecimal digit is also the 0. So for the second text record, the bit mask is E00. So this is the source program. We have the object codes generated here. These represent the relocation bits, and the last column here indicates the bit mask. We shall now see the object program for this particular segment. So the program name is copy. Here it is copy. The starting address is 0 and the length is indicated after that. The first text record should keep the first 10 instructions. The first 10 instructions are 140033 through 00002D. So 140033 to 00002D. Now the bit mask associated with this is FFC, and you may see that it is kept immediately following the length indicator. Length is 1E because we have kept 10 object codes. Each object code is 3 byte in length. 10 into 3 is 30. 30 in hexadecimals is 1E. So this is about the first text record. Moving to the second text record, we have to keep object codes from line number 60 through line number 90. And the object codes are 0C0036 through 000000. So 0C0036 through 000000. And what is the bit mask here? Bit mask is E00. So it is E00 and the length of the object code is 15 bytes. So 1, 2, 3, 4, 5, 6, 7. 7 instructions we have, each of 3 bytes in length. 7 into 3 is 21 and 21 in hexadecimals is 15. So here the bit mask is FFC, which means that all the 10 words require modification. E00 means that only the first 3 instructions will require modification. Now we will look into the subroutine RDREC. So here we have the first text record holding 10 instructions starting from 040030 to 38103F. The starting address here is 1039. So we have the starting address 001039 and the object codes are from 040030, that is 040030 through 38103F. 38103F. The length is 30 bytes, that is 1E in hexadecimal, and the bit mask is FFC because all instructions that we have kept in the text record requires modification. Now moving to the second text record, we have the object codes here. That is, the first code is in line number 175, 100036, which requires modification. The last 3 are constants, so they don't require modification. So the first hexa digit in the bit mask is 8. After that, remaining instructions, we have to keep only 4 instructions in this text record. Now the question is, why do we keep only 4 instructions in this text record? Earlier I had mentioned that always a relocation bit has to be associated with a 3 byte segment. If an instruction requires a modification, then it has to be associated with the relocation bit indicating modification has to be associated with the 3 byte segment. Here we examine that there is a 1 byte segment, not a 3 byte segment. So if the following instruction requires a modification, then you cannot keep this instruction in the same text record. It has to be kept in the new text record, because since this is not a 3 byte segment, the relocation bit will not align perfectly with the following code. So what we need to do is, if at all we find a segment of object code that is not in 3 bytes in length, then we have to stop the text record, writing the object codes into the text record at that point, and initiate a new text record for the following object codes if the following object code requires modification. Now in this case, although we have a 1 byte segment here, the next object code is 001000, which is a constant. This object code doesn't require a modification, so we can write this in the same text record. But the following code is 040030, which requires a modification. So for this cannot be written in the same text record. We have to initiate a new text record for 040030. So that is the reason why we have to stop the text record at this point. The only reason we can write the object code 001000 in the same text record in spite of having a 1 byte segment here is the reason that the following object code doesn't require any modification. So if at all this object code required a modification, then we have to write it in a new text record. So now, having written the first 10 instructions into the text record, we shall see the second text record. The second text record contains object code starting from 100036 through 001000, and the starting address here is 1057. So 1057 is the starting address. Object codes are 100036 to 001000. Bit mask is 800. Only the location bits are available for the first four. We don't have rest of the instructions. So relocation bits corresponding to them are cleared to zeros. So the bit mask is 800. Note, we have to stop at this point because this is not a 3-byte segment. We can write this here because this doesn't require modification. Now moving to the last subroutine, WREC. We shall see what are the text records generated for this. So in one text record, we can keep at the most 10 instructions. So we have 4 plus 4, 8 plus 1, 9 instructions here. So we can keep entire object code in one text record. And the bit mask here is FE0. Starting address for the text record is 1061. So we will see the object code. And the last hexadecimal digit in the bit mask is 0. And how did we get this 0? It is 0 followed by 3 unused words for which the relocation bits are zeros. So the starting address is 1061. 1061 is the starting address. Object codes are placed from 040030 through 05, 040030 to 05, and the bit mask is FE0. It is FE0. So we are done. This is the end of the program. The program is named copy. It has two subroutines, rdirect, wrec, and end is indicated here. Since we are done keeping all the object codes, this is the end. So we have just seen a new technique for specifying relocation as a part of the object program. So in this scheme, we associate each instruction with the relocation bit, which is set to 1 if the instruction requires modification, and it is set to 0 if the instruction doesn't require a modification. This relocation information is indicated in the object program via relocation bit mask, which actually is obtained by gathering the relocation bits together, and we have seen that each bit mask has 3 hexadecimal digits. So for one text record we can have 12 relocation bits. However, since in one text record we keep only 10 instructions corresponding to the 2 unused words, we set the relocation bits to 0. And relocation bits have to bit mask has to be kept immediately following the length indicator in the text record. So this is the object program that is created for the same program that we have just discussed. So FFC means 1111 followed by 1111 followed by 1100. So this one means that 140033 requires modification. The following one means that 481039 requires modification. Likewise, all the instructions here require modification. Now coming to the second text record, the bit mask is E00 and the expansion is E is 1110 followed by all zeros. So first relocation bit is 1. So the first object code is 0C0036 has to be modified because the relocation bit here is 1. Likewise, the second object code is 481061. Again, the bit here is 1, so the instruction will have to be modified. And the third one is 080033. Again, the bit here is 1, so the instruction will require modification. Now, all the following ones are constants and they are indicated with the relocation bits 0. So 1, 2, 3, 4 constants. So 1, 2, 3, 4 all are set to zeros. So these object codes will not be modified and all the remaining are corresponding to unused words. Having generated the object program, that is a relocatable object program for SIC with the relocation indicated via bit mask, in the object program, we are now ready to look into the algorithm for relocating loader and see how the loader processes this object program. This is the algorithm for SIC relocating loader. The first step involves fetching the program address or the actual load address from the operating system. Thereafter, records are processed one after the other until the end of the input is reached. For every record fetched, examine if the record type is E. If it is not E, whenever the record type is T, the object codes have to be moved into the memory location whose address is specified in the text record plus the program address. However, while the object code is moved, it is important to check if the relocation bit associated with the object code is 1 or 0. So if the relocation bit associated with the object code is 1, then object codes have to be moved at the location program address plus specified address by adding to the object code the program address. On the other hand, if the relocation bit is set to 0, then the object code from the text record, the object code for which the relocation bit is set to 0 will be moved from the record into the location program address plus specified address without adding the program address. So this is repeated for every object code in a particular text record. You may see that the for loop iterates for every object code in the text record. So once all object codes have been moved from a particular text record, the next record is fetched. And as long as it is not E, if the record type is T, the similar processing will continue. So we will now see how this object program is processed by the loader. So each time a record type is T, the relocating loader fetches the length as well as the bit mask, and for each instruction that is placed in the current text record, it examines the relocation bit that is gathered in the bit mask. So for the first text record, we see that the bit mask is FFC and the corresponding relocation bits are 1111 followed by 1111 and 1100. So for initially we begin with the first instruction, that is 140033. So this is loaded into the memory at the specified address plus the program address. So if we assume that the program address is moved at the location program address plus specified address. So if the specified address is 0 and the program address is 5000, then 140033 would be moved into the location 5000 plus 0, that is at the location 5000. 140033 would be moved as such provided the relocation bit is 0. However, here the relocation bit for the first instruction is 1, so we have to add the program address to 140033, and thereby the object code after the load at the location 5000 is 145033. So this is repeated for every instruction which has a modification bit set to 1. However, if the modification bit is 0, like for example in the second instruction, we have the relocation bit for the first 3 instructions set to 1, while for the fourth instruction it is 0. So when the relocation bit is 0, the object code is directly moved into the memory at the address that is indicated in the text record plus the program address. No modification is done to the object code. We'll see how this works for the object program that we have just examined. The program is named copy. We will see how the text processing takes place. So the starting address indicated in the text record is 0. It's a relative value. It is used only for the assembly purpose. This was a value obtained during the assembly time. So the actual load address can be obtained by adding to this the program address, and let us assume that the program address is 5000. So the first code to be loaded into the memory is 140033. The relocation bit associated with the code is 1 because we have the bit mask FFC which has been expanded here. Since the bit relocation bit is 1, It means that the object code has to be moved with this program address added. So the load address is 0 plus the program address, which is 5000. 5000 is a load address. We have assumed that the program address is 5000. So 5000 plus 0 is 5000. At this location, the first object code has to be moved. We will see that it's 140033. However, since the relocation bit associated with this instruction is 1, we need to add the program address. So 140033 plus 5000 will be 145033. So we'll see, we'll take another instruction and see how this works. So whenever the relocation bit is 1, add program address at the location program address plus specified address. That is, add the address 0 plus 5000, that is here, wherein we have to place the code 140033. We have to add 5000, and thereby the resultant code is not 140033, but it is 145033. So we'll take another instruction from the second text record. The text record indicates the load address 1E. Relocation bit mask is E00. The expansion is shown here. The first instruction requires a modification. So 0C0036, after being added with 5000, will be loaded at the location 00001E plus the program address. So 00001E plus 5000 is 501E, which is this cell. Here we have to load 0C0036 after adding the program address, that is 5000, because the relocation bit here is 1. So the resultant code loaded is 0C5036 rather than 0C0036. Following instruction is 481061, which will be loaded in the consecutive location after 36. Here we have 36. The next it is 48. So this will be loaded in the next location. However, here the address in the operand field is 1061. But when it is loaded, we add the program address 5000, so we get 486061 because the relocation bit here is 1. We'll move to the next instruction, which has to be moved in consecutive memory location. The code is 080033. The relocation bit is 1. So again, to this we have to add the program address and load it into memory. So the resultant code loaded is 080033 plus 5000, which is 085033. So moving on to the next object code is 4C0000, and the relocation bit here is 0. So please note, since the relocation bit here is 0, we do not have to add the program address. The object code can be directly moved into the memory. So the object code loaded is 4C0000 and starts in the memory immediately following the previous object code. Moving to the next object code, we have 454F46, which is again a constant. The object code doesn't require a modification, so the object code is moved into the memory as such. The subsequent code is 000003. So again, this doesn't require a modification, so the object code is moved into the memory as such. The last code in the current text record is 000000, which has to be moved into the memory at the address in the immediate next location, which is 5030. So object code has been moved into the memory starting at address 5030. So this is the end of the load for the current text record. So to summarize, whenever the relocating loader finds that the record type is T, it fetches the second data, which indicates the length of the object codes in the current text record, and it fetches the third data, which indicates the bit mask. Now, for each bit in the bit mask, if the bit is set to 0, for example, for the first instruction M0, if it is set to 0, then the object code would be moved from the record to the location program address plus specified address without any modification. We directly move the object code. But the location is whatever address is specified in the text record plus the program address, because this is the actual load address from where the program will be loaded. On the other hand, if the relocation bit is set to 1 for the corresponding object code, then before moving the actual code into the memory, the program address has to be added. So program address will be added to the code that has to be moved into the memory location. So also the object code will be moved into the location that is specified in the text record plus the program address. So after all object codes have been moved, the next text record will be read, and if the record type is T, similar processing is done. And once all the records are processed, the relocating loader jumps to the address program address and initiates the execution. So I have an assignment to you. So consider this SIC program. This is a program that is written using SIC instruction set. The program indicates the starting address 0. You are required to generate the complete object program for this SIC program with the relocation information indicated in the object program via the relocation bit technique. So the question is, generate the relocatable object program for this SIC program using the relocation bit technique.